can be fitted in several different ways and easily determined from the sperm. And this is what I show with the two students and of mine in this paper, which has just been published in the Journal of Analytical Chemistry a few months ago. Why one does the thing this way? Because in this way, one avoids making a priori assumptions about the behavior of the calorimetric fluid in the presence, essentially, of what you expect to be new and strange phenomena, such as those of cold fusion. I think this is something to be particularly emphasized. All right. Now I will talk about the experimental work, which consists of a couple of campaigns of measurement, which lasted about 3 months each in the last year and in this year, 95 and 96. The electrolytic cells, well, which I will show picture, is this way, has this electric arrangement. There's an anode, which is a platinum wire, which is 20 centimeters long and 0.5 millimeter diameter. Then there are two power supply voltages. One is called anode cathode. Then there's a cathode here, which consists for blank cells. Well, you will see that I have used here a term which was deemed to be improper by the editor of the Journal of Analytical Chemistry. Blank cells, of course you know what a blank cell is, but maybe you don't know what a black cell is. Then he said, well, what do you call a black cell? Well, that's the opposite of blank cell. Really? Yes. Because I believe that blank comes from the French blanc, which is white. So the opposite of white usually is black. So he was convinced. So the blank cells will have a cathode which consists of a 500 centimeters wire of palladium in the black cells, and in the blank cells platinum, 50 micron diameter, but in the first campaign this length was shorter, almost a factor of 2. So this is the thing. And also you will notice here that you have two power supplies, what we call V anode cathode and V cathode. The reason for this electric arrangement is essentially the kind of it is the basic ideas of what I'm talking about, and this is why I tried to do my own measurement due to the fact that in so-far in cold fusion, this arrangement hasn't been used. Now, the first campaign of measurement, which is reported in the paper I just mentioned, we discovered with great surprise that black cells, which were physically exactly the same as the black cells, with the platinum wire instead of the palladium wire, behave thermodynamically rather differently from the black cells. Let me show you what I mean by that. So, right, so this is the scheme of the cells. Notice that I have 3 thermistors because I wanted to check at different heights the temperature, and whether if these cells were really well mixed and so on and so forth. So we found some gradients, not very severe, but this allowed us essentially to make the corrections to the simple isoparabolic, to the simple formula I showed to you. So this is a typical black cell. Talking about dozens of experiments, this is one of the dozen experiments we made. So that is the A coefficient, and and we get the measurement every time we have a pulse, and we determine it, and then we get this with it. Now, when this is converted into an efficiency ratio, Wx over Wn, you get something like that. So you see, typically you get an error of the order of 10–20%. But as I told you, we are not really fishing for something much more accurate. That will take much more time, and this will be done, of course, in due time. But I think this is something that ought to be taken into account, kept in mind. Now, when we have this exactly the same arrangement with black cells, this is what you get. So you start with something which is similar to the black cell, some dissipation coefficient which is similar to the black cell, and then a certain point when also, you know, by looking here, the cell starts being black, you get a different pattern of dissipation. This, of course, you can imagine the sleepless nights that this entailed, because you don't get this kind of disaster very lightly, of course, because you know, thermodynamics is supposed to be thermodynamics. Everything gets mixed in. You will see actually before the end of the talk that we found out some plausible explanation for this. So you notice here that we get efficiency in the order of 80–90%, which meant with those cells something, you know, power excess in the order of 100 watts, which between 50 and 100 watts, which meant for the kind of system we had, power density in the order of 5 kilowatts, which would be centimeter. Something essentially in the same ballpark has observed by Fleischmann and Pons in the course of the experimental program. In the second campaign, this is the paper that has been presented at this conference, this finding has been completely substantiated. Let me show you two typical. So this is a black cell. This is just the power in, and this is the profile of the power, excess power. Okay. Same thing. Excuse me?
Can you focus that? Can you tell us what?
I would like to, but I don't know how to do it.
Is the plotted there?
Is that all right?
What is the plotted?
Here is just this coefficient A that I defined in the previous slide. Here the power, this in red is the power, the input power, and in blue here, or in violet or whatever, in purple, is just excess power.
The exercise time?
And this is time, yes, that's a function of time. When we go to a black cell, and this is not really the best example I have, but it's just one example, then you see that first of all, at low values of current, of course, and also input power, you get the same kind of dissipation. Then by the time you go to higher values for the input power and the currents and the potentials in that electrical arrangement, and you find out that this changes. Now when you calculate excess power, you know, one thing that really strikes you very much is say you throw in your parts, your heat parts. Then say in the black cell, in equal conditions. So in the black cell, so the temperature goes, has a certain tension, will go asymptotically, say, it will rise a couple of degrees. In the black cell, it's half that much. And that is really something which is mind-blowing, at least in our arrangement, and you have to understand it. Well, I think we understood it when we tried to make a more conventional analysis. So let me go to the final part of this talk that deals with when we decided to embed our cells in a flash calorimeter after having shielded the cell with a copper plate in order to convert possible outgoing soft X-rays. Because we had, from a very preliminary analysis with the dental field, the medical field, we had also evidence, the kind of evidence that Daniele Gozzi presented a couple of days ago. And so therefore, just to make sure that, you know, that we capture the excess energy in strange new ways, we in fact insisted to do that. Now, the calorimeter I'm talking about has this structure here. It is embedded in a door, which is highly insulated with all kind of glass wool and other materials. And this is essentially the structure. The cell is here, and it goes on this way. Unfortunately, I cannot go ahead. So the experimentation began a few days ago, October 1st, and this is what we saw when we began our experiment. So you see, all right, so now let me show, yes. Okay, so maybe I should, do I have some laser light here? Yes. So you see, this is just the beginning. Then we turn the power on. We initiate the electrolysis, and then we see that the flux calorimeter output, which is just here, just the red light goes up. And it has a typical 200-second time constant, so it will go to this place. But then we see that when it just was projecting, you're going to go this way, then it starts going down. And at the same time, the monitor of the resistance of the wire shows that the resistance is going down. So this means that that is a signal, as you know very well, of loading, okay? At least in an average sense. Then I'm just making a little lecture to my collaborators saying that this, even though it doesn't seem to be that way, might be an evidence that something strange in the way of cold fusion is happening, just because of this new escape route. Then a collaborator of mine who just set up the calorimeter goes to the calorimeter and adds a lot of insulating materials just in the outgoing, in the escape route of the gases. Then the temperature difference goes up, and therefore the reading of the flux calorimeter goes up. And then I say, I didn't know this operation. I say, okay, now it's going up. Actually, we're also making now isoperiodic calorimeters, as you see with the steps, and we can check this also in the other way. So we have two parallel methods to check this. But then the same collaborator goes down and takes away this insulating material and this something which is deemed to block the escape routes of this thing. Everything goes down again, then it goes up, and then. As you see here, we're putting in here 80 watts and getting 170 hours. That's the first thing. But then we have a power failure. This goes down. The wire deloads, and when it starts out again, here, you see that you have lost the effect. And in fact, when this happens, you have to change the wire and do something to it. And you see that this also would be here and here. It's just, and we have other experiments which show that our calibration are good. Certainly the error is within 10%, because we don't want to do much better at this time. We only want to validate the idea. So this is the story. So the sequence of these events.
Could you?
Yes, I finished. That I have just described shows that the gas escape route, and also the possible blocking of X-rays is very important for black cells. And also the analysis we made in parallel of isoperiodic calorimetry yields a lower bound for WX. We find out that the power we estimate, the excess power we estimate, is between 20% less than what we calculate, than what we determine through the flux calorimeter. And also, we've shown that when a black cell has good reason to become blank, both calorimeters register such an event. So I come to the conclusions. So on the basis of these two campaigns of measurement, we turn out to be coherent in a vulgar sense, not in a complicated theoretical sense. On electrolytic cells in a new electric configuration, we can state that the electrolytic cells in the new electric configuration produce large quantities of excess heat. The efficiencies are typically between 100 and 200%. The excess powers that you produce with this kind of cells are in the order of 700 watts. And power densities, due to the fact that a 500 meter wide is a tenth of a centimeter cube go easily in the range of 50 to 100 kilowatts per cubic centimeter. So on the basis of this, I may conclude with this statement, and let me take the occasion of thanking you very much for your patience.
We are quite late, and I think that we should allow for a few questions. Any Legozzi?
Giuliano, can you give us more details about the electrical assembly of your system?
Well, yes. First of all, the concentration of electrolytes is very small, very low. Between 10 to 5.
Electrical.
And the electrical thing is just, you have a power supply which maintains a constant potential difference, of course positive, between the anode, which is just 20 centimeters of palladium wire, 0.5 millimeter diameter, and 1 point of the cathode. This typically we work with potential difference between 50 and 350 volts, anode EAC. Then we worked with different configuration at the cathode. One of them, VCC equals 0, which is what Celani was talking about yesterday about the collider. But this collider is a metaphor, because you don't collide anything with this potential, of course. And in the sense that you have a kind of a closed ring where you have only the electrolytic current, which of course creates large potential differences. Across this ring. Excuse me?
Not only with the current.
Well, the current, due to the fact that you have a high resistance, the only fact that you flow current creates a potential difference, as you know very well. Excuse me?
We have dial to get extra current. Explain you several times.
Yeah, but it doesn't matter. It doesn't matter. We are talking about the general. It doesn't matter about the details. What is important is the eye of mind idea, which you tend to have somewhat close. It's pretty important to realize that there is a new effect, a quantum mechanical effect, which leads you to electrochemical potential. And that is the important thing. I don't care about diodes. Right. So the other thing is, of course, this cathode potential, which we have run all the way up to 500 volts along the 500 centimeters of the wire. So we have done, and also very important is to have an electrolyte with a very small concentration, otherwise you're burning everything. And the concentration we have used ranges between 10 to the minus 5 and 10 to the minus 4 molar, LIOD, of course. And this again is just according to the teachings of Master Fleischmann.
Dr. Harrison?
Thank you. Welcome to the world of experimentalists and power failures.
Experimentalists
and power failures.
A power failure?
Yes, it happens all the time.
Oh, sure. Okay. So you know what the lights of that are.
In your abstract, you say you're going to do the experiment with heavy water and light water.
Yes.
And you compare it with theory. Now, you didn't actually say whether you used heavy water or light water. Was it heavy water?
No. I have used always heavy water because I didn't want to change when I was comparing. Also, I run a lot of experiments, twin experiments, when I have precise, we have precisely the same power supply to the two cells, one the black and the other. So I didn't want to change too many things, so I changed only the black and white. But I also work with light water.
And you found what?
I can't say.
Well, if you
not only Martin, is allowed to be cryptic and, in his faith. I'm imitating.
I quite understand you kind of say the experimental results, but since you have your theory for some time, you found 200% excess heat for deuterium. What percentage do you predict for deuterium, and what percentage do you predict for light water?
Okay. So as far as palladium is concerned, I believe that if you run with light water, you will get essentially zero. If you have something else, maybe not. In fact, it certainly seems not to be the case. And this is why I'm not giving out results which I'm not sure of yet. So that's why I was drifting. But about the theory, well, I am in the right ballpark. It depends, it depends on what is the correlation, what is the coherence structure of the domain where you have cold fusion happening according to the theory. Now, if these domains are very small, I mean the smallest, I concluded that you get something in the order of a few hundred watts per cubic centimeter. So this really is telling you that you are reaching, I mean at maximum, that you're reaching a situation where you have a long-range correlation, coherence within the plasma of deuterium inside palladium. Now, palladium may be very, very peculiar. If you go to nickel, maybe you have something else. Actually, what I tried to do, I mean, theoretically, it was not so much to go into the details of a complicated structure, but at least to clarify the concepts. And one of the concepts was that in such an electrical arrangement, I should have a high increase in the electrochemical potential. And the results that are presented today seem to go in that direction. So I think here we should really be very careful as far as theory is concerned in demanding too much to the theory when you are dealing with an object which is awfully complicated. You just have to look at the micrograph of palladium to see, I mean, how Storm aptly and correctly showed, I mean, how variable your system. So when you talk about reproducibility, you have to take into account that reproducibility with something which is totally irreproducible in microscopic terms. It's not like particles that you and me, that you and I love and cherish, where you have a very little variability in the thing you do. So, and to that extent, I think the theory fared pretty good.
Thank you for your answer.
Well, I think that our duties to finish this session force us to interrupt this very interesting discussion. And I thank again Professor Preparata for very exciting talk. This talk ended the present session, and the next session will be chaired by Michael Nakuda. And Dr. Schneid.
Yes, we'll move on to the second half of the morning session, and the panel will be Access Heat 2, and let's welcome the chairs, Dr. Makoeto and Dr. Mallove.
Now, let's go on next session. The next session is access heat. We will have two scheduled papers. I am Numata, chairman of this session, and co-chairman Dr. Makoeto. The first paper
My name is Hideo from Inland Japan in Hokkaido. It's my great pleasure to talk about our recent results of excess heat measurement based on mass flow calorimetry at high cathode loading. As you can see, we reported at ICCF-6 that excess heat was observed in the electrolysis of one molar LiNOD using palladium cathode from various sources in the fuel cell type closed cells. Depending on cathode loading ratio and current density, their critical values lying around 0.8 and 0.1 to 0.2 ampere per square centimeter, respectively. On the basis of these results, we have developed mass flow calorimetry system in order to increase reliability and accuracy of the measurement. We have further investigated the experimental conditions for the high cathode loading, at which higher excess heat would be expected, as the maximum D over PD was only 0.86 in our former results. Now, I'd like to outline my presentation. First, I will explain our mass flow calorimetry system and electrolysis cells and other experimental conditions. Next, I will talk about the experimental results of the excess heat measurement with palladium and palladium-rhodium alloy cathodes. Finally, I would like to discuss about our present results. This here shows our mass flow calorimetry scheme. The flow rate of cooling water around 20 degrees centigrade was controlled about 0.55 gram per second. And inlet and outlet temperatures of the cooling water were measured by platinum resistance thermometers, which have 0.01 degrees centigrade in resolving power. The output power was calculated using these parameters, inlet temperature and outlet temperature, flow rate, and specific heat of cooling water. We used two types of electrolysis cells. One is the field cell type cell, and the other is the electrolytic type cell with an internal recombiner. Both types cells contain inner and outer chillers for heat exchange, and a heater or platinum electrode for heater calibration before and after electrolysis. We compare the characteristics of the two types of cells in this table. You can see the difference in anode and the reaction on the anode. Gas phase, the procedure for the cathode loading measurement, and heat sources in the cell. I will briefly explain each method to determine the cathode loading ratio. One is from decrease of gas pressure during electrolysis in the field cell type closed cell. And the other way is by cathode resistance measurement, which was employed in the electrolytic type cells. We converted resistance ratio to D over PD using our original calibration curve, this red one, reported at ICCF-6. This figure shows the basic characteristics of our flow calorimetry system. The relationship between the output power and the input power obtained by heater calibration had good linearity from 0 to at least 30 watts. The heat recovery efficiency K was about 0.99, and it remained constant for several months and was not significantly influenced by the nature of the heat source. Excess heat measurements have been conducted under the experimental conditions briefly described on this OHP. You can see here materials, pre-treatment, electrolysis, electrolyte, and electrolysis protocol, and so on. And this is the summary of our experimental data for 26 cells conducted by varying cathode materials and pre-treatment. The maximum DO/M and corresponding current density are given in these columns, and the results of excess heat measurement is given in the last column. I will show you the typical data of these experiments, EFC41, EFC46, and EFC50 in more details in the following figures. First, this figure shows time dependence of current density and cathode resistance ratio R/RO for EFC50 experiment using 39 purity palladium cathode from Imra materials annealed at 1000 degrees centigrade for 24 hours in vacuum. Electrolysis was started by applying a step-up current mode. The resistance ratio went through a peak of about 2.0 and came down to the minimum, corresponding to D/PD equals 0.91. And after the reload cycle, slightly higher value of D/PD of 0.9 was obtained. And during this period of step-up current mode, the total input power was kept constant at about 10 watts, as shown in this figure, while the electrolytic and heater power changed. The thermal balance during this period is shown in this figure, which tells us excess heat was not observed. There were barely any flows crossing beyond plus minus 3 sigma lines defined by the heater calibration. This data is interpreted in terms of histogram as shown in the next figure. The histogram of excess power as shown on this OHP has normal distribution around 0. And this shows again that unusual energy balance was not observed in this experiment. Next, the experiment EFC46 using 49 Johnson Master palladium annealed at 1000 degrees centigrade for 24 hours gave better cathode loading after applying anode stripping, as shown in this figure. The maximum D over PD of 0.94 was attained around 0.2 ampere per centimeter during 2 consecutive step-up modes. However, the heat balance during entire period shows no sign of excess heat as shown in this figure. We tried the ramp mode electrolysis up to 1 ampere per centimeter after the step-up mode as shown in this figure. Although the cathode loading tends to decrease at higher current density, D over PD maintained a value around 0.88 to 0.89 at 1 ampere per centimeter. The heat balance during the ramp electrolysis, however, did not give any sign of excess heat, as shown in this figure. Next, I will talk about the data of EFC41 experiment for the palladium rhodium alloy cathode containing 10% rhodium in a field cell type closed cell. The cathode loading ratio D over M increased with current density and reached about 0.99 at about 0.5 ampere per centimeter. Although the loading ratio close to 1.0 was attained at relatively high current densities, no excess heat was obtained according to the thermal balance shown in this figure. These large spikes appear upon stepping up and down of current density, because in this experiment, no heater power was used to keep the total input power constant. And finally, I will show you the statistical analysis of our measurements in this OXP. The maximum cathode loading ranged 0.82 to 0.99. The statistical distribution of which is shown in this figure. The current density and cell temperature for the maximum loading varied, as you can see here. Unfortunately, however, we have not observed excess heat in any cells within experimental errors. we have tried to interpret present results obtained for palladium cathodes and previous data in order to show excess heat in terms of the cathode loading and current density. We plot the maximum D over PT for a given current density for each experiment. Blue points for the present results and red ones for the previous data. The cathode loading has been greatly improved compared to the former results, as you can see in this figure. While no significant excess heat has been observed for the improved conditions. This may be interpreted. One, some unknown factors, in addition to the cathode loading and current density, may be operating for excess heat generation. And sensitivity of mass calorimetry system may not be high enough to detect anticipated excess heat for the cathode volume. And three, accuracy of our former excess heat data may need to be investigated. Our new research plan for excess heat measurements is based on the above interpretation of the present series of studies. Thank you very much.
Thank you very much. Now this paper is open to discussion. Please. Dr. Morrison.
These results from IMRA in Japan find no excess heat, but yesterday we had results from IMRA in Europe that did find excess heat. Could you comment on the difference?
I can answer.
Okay.
It seems to be that there is a lot of variability in whether the excess heat is seen or not seen, depending upon the apparent batch of crystals that are used. In particular, the SRI group had great success with particular kinds of crystals, and with other kinds of crystals they did not. I was wondering if you tried to correlate the success cases with batches of crystals that you had from a common source, as well as if there has been an examination of the former crystal structures, a sort of post-mortem done of when things worked versus when they haven't worked. And if you haven't done that, it might be a good idea to do it. Do you have any comment on that? Okay, that was too fast. What I'm saying is, it's not just loaded, it's the crystals. And if you look at the crystals and try to examine them, you might find out something.
All right.
Okay.
So answer to the question.
Okay, Dr. Kunimura, please answer.
Thank you very much for that comment. It's very difficult to answer that question, but our principle, our concept in the excess heat measurement is based on the high cathode loading, whichever crystal it is. So we haven't compared various palladium crystals yet, but according to our data obtained up to date, we haven't found significant differences among the crystals. So we have been concentrated on the electrolysis conditions for additives to have better loading. Thank you.
Please wait, Dr. Okamoto.
I have two questions. I think,
Dr. Okamoto, next.
Okay, if I have well understood, in this new experiment, the main effort was to keep the power input, means the total system, as stable as possible. Because when you increase the current, you decrease the heater and so on. So it means you try to make almost zero the variation of the system. So, but before several people in the previous experiment make an effort in order to have as much as possible non-equilibrium condition. So my comment, and looking for the data about cold fusion, when you have constant condition, you never get HFIT. Just pretty much my data about 3 years before. In that data, we have a plate that gave a very large loading. So what we found, during the loading at the maximum about 1:1, we get HFIT. When the loading was stable, our HFIT dropped to 0. So we see something wrong in our system. But after we realized that in a constant condition, even a very large loading never HFIT happen. Just an example, limiting example. If HFIT is just due to loading, if you can imagine we have a very high pressure system, 1,000 atmosphere and plasma inside, so you have HFIT. But this never happened. Means constant conditions are not good to get HFIT. Thank you.
This is the last question, Dr. Okamoto.
Chira's question every time so long, so I ask 2 points. You showed previous data and present data. In these 2 cases, is the same electrolysis condition, especially the pulse mode or such as stepwise or repetition time. The same? One? Same. Okay. And I want to know the reason you selected such a pattern of electrolysis. But it maybe takes a long time, so.
Okay.
Thank you.
Next speaker, please.
Yeah, I'm afraid we're going to have to terminate discussion there, so thank you very much, Dr. I'm sorry to do this, but you either eat and go on the excursion or continue questioning. The next paper is to be on the achievement of solid-state plasma fusion, cold fusion, by Professor Arata and Dr. Jean. The paper will be presented by Professor Arata.
Thank you, Mr. Chairman. First, I'd like to explain about our conclusion. We have developed VHS cathode in 1992. VHS cathode generated huge excess energy, such as 200 to to 500 megajoule per centimeter through a long period, such as 5,000 hours. All cathode indicated similar results. We have obtained another result, namely a significantly large amount of helium corresponding to this amount of excess energy was clearly detected as deuterium reaction product as an ash released from the high deuterated palladium solid. When it was heated in high vacuum 10 to minus 8 over around 1,000 centrifuge using an improved quadruple mass spectrometer. On the other hand, simultaneous measurement by another QMS detected no signal of the existence of helium-3 and tritium, including its compound. This means that there exists no well-known Lazarov type of the deuterium nuclear reaction within palladium solid, and an inherent feature of solid state with much balanced electron cloud, such as the palladium presents a circumstance for a new type of deuterium nuclear reaction which directly produces helium-4 as main reaction product. In order to prove of a nuclear fusion reaction inside the solid must be clear that two criteria in A and B are shown in figure in this diagram. First, is that the host solid must have continuously created a large amount of excess energy. Second, is that there must be residual product corresponding to the amount of excess energy generated. This is our producer system. Left side shows DS cathode, open type and closed type. Open type cathode can detect in a pressure up about 900 atmosphere. This pressure was limited by only pressure gauge. On the contrary, closed cathode will be rising up some 1,000 bars. Right side is closed cell. Inlet and outlet water temperature are measured by reversely connected some couple, and at the same time, a platinum resistor. And you can see, easily understand. I think left side is principle of our measurement system. I think you can easily understand this diagram, but I'd like to emphasize that the most important parameter is cell power, which includes excess energy and cell loss energy, as defined in this diagram here. This cell power is negative in essence when no excess energy. As you see, this feature should be noticed in this one. Right side is inherent feature of our closed cell and indicates the most important basic data using platinum anode and platinum cathode. Our usual experimental range is around 120 to 150 watts, and the cell power is clearly negative with about -1 watt as you see here. Our old data were obtained by only changing the platinum cathode to a PS cathode. This shows two examples with a huge amount of excess energy generation at present state during generation. All other cathodes demonstrated similar results. Generation pattern of each sample is significantly different like this. But total energy almost similar. This diagram is an example of open-type DS cathode. In order to study the dynamic behavior of the inner cathode, open-type DS cathode was used. This diagram demonstrates the startling phenomenon. This is the inner pressure. This is elapsed time. And this is the cell power, so-called excess energy, minus velocity. This is the pressure, and 2 hours stop per off, and suddenly decrease inside pressure, and like this, and on, switch on, and suddenly does up. And this is cell power, almost excess energy, like this. And so it looks like correspond to the pressure. We are now thinking about that behavior of inner pressure, TC, plays a key role as one of the most important factors to achieve cold fusion. It is considered that generation of these phenomena depend on characteristics of spillover deuterium. In right side diagram, deuterium concentration inside our cathode A and inner cathode, paradigm black B, are significantly different. A is controlled by Siebert law. B is controlled by spillover effect, which breaks spillover Siebert law. This reason is that when A is 90%, inner deuterium pressure is required over 100,000 atmosphere. On the contrary, B is almost 100% instantaneously if within 100 angstrom in size, such as so-called atom cluster. By the way, in our paradigm black, inner deuterium pressure may be some thousand atmosphere. Left side diagram demonstrates long incubation period, A0, B0, here, which is explained by only spillover effect. Consequently, during this incubation period, deuterium comes only to paradigm black rather than vacuum space. such as a particle gap. This is a principle of GS cathode. This diagram shows us three kind of quadrupole spectrometer system, which is essentially required to detect. That is the helium. A is ordinary type. Then exists test gas flowing through a QMS zone. Using this system, it is extremely difficult to accurately detect a chronological change, which is the most important feature of the helium. Because this flowing gas system requires much crystal gas, many pollutants are accompanied, and it cannot be eliminated from the QMS zone. By this reason, both accuracy and reliability, which are basically the most essential feature of mass measurement instrument, should be significantly get down. Anybody who did not take care this byproduct such a pollutant helium, having suddenly misdetected as helium released from cathode. We studied long time about this pollutant helium in this early stage. We want to stop of the cold diffusion research when we saw much pollutant helium. This is the inside in the lubricant of molecular tone and non-metallic material such as ceramics and quartz, etc. Many pollutant helium exist. However, because improved QMS was accomplished, we could continue to the research. Namely, we developed the BNC type. B type is fine control to back pressure of QMS. We call the limited QMS, and by which we obtained many excellent data. Thus, we arrived at the final stage as the closed QMS, which is constructed by only sample vessel, get at home, and the QMS. In other words, closed QMS is completely separated from other systems. This is limited QMS. I'm also, my hand is not so good, so I can't remember. This is a limited limited QMS. This important point is sound vessel, and this exhausting system, limited QMS, is 2-point very important. And this is closed QMS final stage. This is a molecular pump, beta pump, and sample vessel, and QMS 1, 2. So closed system, that is only this. And this one, closed QMS principle. And closed vessel here in the sample, and exhaust gas, and initial condition in pressure 10 to minus 8, and keeping time 5 over 15 hours, around 10 hours need, because must eliminate product. And QMS start and close, so-called closed QMS start, and residual gas appear. Sample heater start in the right step up condition, and get up home. The same time. And this chronological chain can be detected over all stages. And residual gas remains in just the state of any numbers of days, especially helium. So repeatedly pump or can detect to concur anytime. Chronological chain with increasing temperature can be partially affected.
Professor, ask 5 minutes.
Okay. Get up action, no pollutant. Get the action, no wax or helium. But pollutant affect people, strongly affect. Okay, this is a historical result. And this is about 1 year old published. And this is also background, and it's a sample. And this is without non-deuterated deuterium, without sample like this. This is a pollutant, and also with sample. You can see helium. This is also said, but a different sample. And this is a very beautiful helium, only helium and deuterium mass hold. And this black zone at the original site, like this. This is a blood test without sample and with sample room temperature, and deuterated sample. This is the most victim so compared. This is also so reheated. The first time heated, and so the solid remove this gas. After that, the heating you can see that clearly. And this also closed of QMS. This is also non-deuterated sample. This is a deuterated sample. Another sample. Also, this is a very detailed detected. And so, this after this results, helium, deuterium, 10⁻², exactly so inside. And finally, this is a very important result. And this is trend data. This portion get after students only here, and this sample with sample closed start like this. And this is a get upon action like this. This is a get upon action, and this heating start like this, and this 15 hours elapsed like this, or almost so helium, not deuterium, almost diminished. So this point M4 also expanded this one, and helium-3, no, M3 here. And almost cannot get helium-3. For example, resolution, this product vessel, product elements, and sensitivity like this. Helium-4, and here you can read, and helium-3 like this. No, sensitivity of product QMS, high resolution, and like this 0.3 ppb, and normal 0.003 ppb, and very high quality. So this is indicates the trend curve. If helium like this almost constant here, like this here, and but polygon, for example B2 or DH, and like this. This is no helium, and so this is a beta action. So,
thank you very much. We're running rather short of time, but if there is one or two pressing questions, Dr. Rashid.
Was it a question or a comment? May I tell you that make you a wish? Yes, it appears to me that your data are probably, at least to me, the best proof for the existence of helium. I would urge you
to make a calibration of apparatus in order that all the community can benefit to knowing exactly the amount of heating recovered and to be able to compare with the heat excess. And thank you for your work.
Thank you for that comment.
First, also a comment. Your palladium black material is ideal for checking the swimming electrons, supervised electron. Black material, yes. And from the numbers I write down yesterday from your poster, I get from your results that a distance of interaction is 2 picometers, fully in agreement with similar results. But now my question, the calculation would result in 2 or 3 times higher energy output than you measured the calorimeter. Is it possible, is my question? Is it possible that your calorimeter takes only, so to say, energy gammas inside, and half of their energy or more is then getting outside into space and is not being recovered? This is my question. Do you consider you have hard gammas and most of the energy is then going out of your department?
More simple, you say. Simply, I ask you. Gamma. Gamma ray. Gamma ray. Not yet. We get gamma ray.
We'll take a final question from Talbot Chung.
Well, I just wanted everybody to be clear that you were showing spectra of repeating spectra of mass 4 showing helium-4 and deuterium as you heated these palladium pieces of palladium powder up to 1300 Kelvin, and that you also showed very high resolution analysis of helium-3 versus DH plus as a double peak structure, except that you didn't find any helium-3. That's really what you were showing, right, in the mass spectrometer studies. You were showing thermal desorption data on palladium powder that had produced 25 kilowatt hours of heat, and also palladium powder that had not been exposed to deuterium and which showed no evidence of helium-4. Is that not correct?
I believe the answer to that is correct.
Okay, I just wanted to
we must close the session or we're going to miss the excursion. I believe the Secretariat would like to have a word to you. But
Thank you very much.
I forgot to. Can I have a slide? Oh, it's just a very simple slide. I forgot. One. Take the light off, please. A little humor. Guess who's this one? No, can you please get the light off, please?
Sorry, before that, let me say that the bus will leave at 1:45 for the excursion, so you don't have to rush that.
This is very good, Professor. Oh, guess who's got mine?
And tomorrow's morning session will start at 9. And let me say, for those attending the excursion today, the bus will leave at 1:45. So we would like to take a quick lunch, and after that, please gather in front of the tour reception desk on the first floor lobby, and pick up your badges there. Also, please, as I did this morning, please submit your proceedings by 2 tomorrow. And do remember that the banquet starts at 8 tonight.